Hello, everyone. Today, Steve and I will present how we at Twitter migrated one of our main revenue data pipelines for analytics into the Google Cloud. My name is Fabian. I am the tech lead for the revenue data pipelines team. My team is handling the ingestion, transformation, and aggregation of raw revenue data. And we then ingest that data into various data stores where it will get picked up by various downstream systems. With me is Steve.
Hey everybody, I'm Steve. I'm the tech lead on the revenue data analytics team at Twitter. We basically pick up right where Fabian's team leaves off. So we handle storing and querying all of the analytic data that's been processed by his pipelines. So let's just take a step for a second and talk about advertiser analytics at Twitter in general and the things we do. So as Fabian mentioned, we take raw impression and engagement events. So an impression is just kind of like someone viewing an ad, things like that. Engagements are people actually interacting with them in some way. We take those from a variety of sources, client devices, our internal systems, a lot of different things, and run them through various pipelines that will filter and normalize that data. So then we take that normalized data and we pre-aggregate it. So why do we pre-aggregate it? Mainly for performance reasons. The scope of the data that we're running on is so high that it would be infeasible to actually do it on the query side. So instead of doing that, we do it at ingestion time. So we'll take this data. It's fairly highly dimensional, and some of these dimensions have a lot of cardinality, which has caused problems with just some like off-the-shelf systems and why we have to build our own pipelines to do this. We'll take those results of these aggregations, and we actually store them in different data stores. So the way we do this, the storage is generally based on query patterns that we observe, things like that. So just talk about the scale of what we're doing this at, so everyone has an idea. Again, like I said, every ad and impression event we have flows through the system. So that's something like on the scale of about 20 terabytes of log data a day. That breaks down to around 100,000 events a second that we're processing. On the serving side, from how we're actually taking this data and using it in a useful way, it's somewhere around like 5,000 queries a second that we're actually serving. And these can range from simple queries of give me the last week of spend for an advertiser to give me the last 3 years of data broken down by geography or impressions or things like that. So the query complexity can be a very high range of stuff. Typically, we have an SLO of around a 1 second P99 latency on these queries. Typically, we run around 300 milliseconds. So that's what we target for these queries.
So before we go into the system that we are building and have built, let's look at our legacy system, how analytics aggregations have been working at Twitter for the past few years. So the legacy system is a Lambda architecture consisting out of a stream aggregation system and a batch processing system. Basically, the flow for both of these is we're having raw logs that are ingested by one of the streaming systems, by one of the aggregation systems, and then aggregated and stored in a key value store. The serving side, so when advertisers want to query how well their ads are doing, they're hitting our serving front end, and that serving front end will then reach out to the key value stores and fetch the data that they're requesting. So we have our stream aggregation pipeline is approximate. That means we're subsampling some of the data, so we're having too much data to aggregate it on the fly in the current system. And also, our current streaming system only supports at most once delivery, which means some data is getting dropped. And so this is not a good system to bill people for, or in general, it's just an approximation of the overall data. Which is where the batch processing comes in. So just for reference, the streaming system has about an end-to-end latency from ingestion to serving of about a minute or two. On the batch layer, we are processing all data and not doing any sampling every 4 hours for 4 hours of data. So that means the batch system is about lagging 4 to 8 hours behind. The batch system is authoritative and persisting the data into a persisted key value store. So when the serving front end is querying for data, it will try to fetch the data from the persisted key value store. If it's not available, it will try to fetch it from the ephemeral key value store that has the approximate data. There's some obvious disadvantages of running a system like this. Number one, we have two very different technology stacks. We have a stream aggregation system, and we have a batch aggregation system that uses very different technologies, and that's a lot of operational overhead. There's another problem that while business logic between the two systems is shared, it is not identical. For example, the sampling of data is only implemented in the stream aggregation, which then makes it very difficult to validate the stream aggregations versus the batch aggregations. So there's some validation overhead there. The biggest problem that we're facing is that the system is about 5 to 6 years old and has reached its design capacity. So we're reaching a point where we can't just throw resources at our current architecture in order to scale it up. And in order to keep up with Twitter's growth, we need to build a new system. So what problems are we actually trying to solve? Our project goals are to reduce the operational complexity and really fundamentally decouple business logic, aggregation from data storage, and query execution. We also would like to increase our data accessibility, really making our data accessible at every part of the pipeline and inspectable. And then we need to plan ahead and have a system that can run at 5 to 10 times our current scale, so we have some headroom and don't have to go through this exercise anytime soon again. So this is what we envision the future looks like. We want to build a Kappa architecture, a first-class authoritative stream aggregation system, and with multiple storage backends that allow different use cases. So like a quick walkthrough, we have the raw logs that are getting ingested into or getting pulled by some stream aggregation system or ingested by a stream aggregation system, and then write it into BigQuery and BigTable, or stream it into the aggregated data into BigQuery, BigTable. The BigTable data store is going to serve as the serving front end for very similar to our existing use case, where our advertisers will be getting served data from there at very low latency and high throughput. On the BigQuery side, we want to be able to allow for internal use cases and also for future development purposes, allow access to the aggregated data and to some extent the raw data on a very low level and very flexible query layer. SQL is a great language that allows you to slice and dice data however you want, and that's one of the primary reasons we want to start using BigQuery for this use case too. So building this streaming first system is great, but we need to find a way how to migrate our legacy system into an environment like this. Our current plan and what we are building right now and have built and looks like this. We're ingesting raw logs into HDFS. We have then pushed those HDFS logs into BigQuery using an internal tool. And then in BigQuery, we're using BigQuery as a data warehouse and as a processing engine, ingesting the data into BigTable, where it is serving our clients through the serving front end. So why are we doing the batch layer first? And that has a lot of there are a couple good reasons for that. Number one is like our current or the legacy batch layer is the only system that actually implements the full business logic and has all data available. So in order to be able to validate what we have built, we needed to go through a process that we could validate against. Furthermore, validating data in BigQuery is much easier than through a streaming system, for example. Using BigQuery really allows us to inspect the data and validate the data at any step in the process. And it makes the discovery and implementation of business logic much, much simpler. So it allows very fast iterations on implementing business logic. So let's look at how we are ingesting data into BigQuery right now. Specifically, our raw logs are stored on HDFS in serialized thrift. We generate about 1 terabyte of data an hour of raw logs. And we built an internal tool, a Hadoop library called BQ Blaster. I think there was a presentation about this one earlier today that went in a little bit more detail. That tool will take the serialized thrift data, convert it and transcode it into Avro, and then write those Avro files to GCS, Google Cloud Storage. From there, it will be picked up at the end of the write, still part of the MapReduce job. It will kick off a BigQuery load job, one partition per load job, so we can load a lot of partitions in parallel and a lot of data in parallel. And we're using BigQuery load jobs instead of the streaming API because BigQuery load jobs are cheaper to run, and we're not really worried about end-to-end latency for this project in terms of in the batch ingestion. So why are we using BigQuery at all? And I mentioned that a couple times before. Like, we're using BigQuery here as a data warehouse, and it's a very performant data warehouse that scales very well. It's capable of ingesting terabytes of data an hour. All data is queryable and inspectable at all times. Because it's SQL and has a SQL front end, you can just write queries just against any other SQL database and get results and really interact with your data, huge amounts of data. BigQuery inherently has a very good separation of storage and compute that makes scaling very, very easy and gives you a lot of control of what you want to scale and how you want to scale. The SQL interface allows a very fast, iterative development process and really forces the separation of concerns. So you're really forced of separating your business logic from your other system. We are not using BigQuery in this implementation only as a data warehouse, but we're also using it as a processing engine. In this case, we're placing some of our MapReduce jobs that are running in our Twitter environment. So the way we're doing this is after we're ingesting the raw logs into BigQuery, we are scheduling jobs that run a set of SQL queries, which then output the aggregated data into another BigQuery table. These scheduled jobs are, whether they're scheduled or triggered, they run in a scheduler. Think Mesos Aurora or Kubernetes or Google Cloud Composer like Airflow. And whenever there are new raw logs available, these jobs get kicked off and first normalize the data using a SQL statement, and then aggregate the data, also using SQL. And then the output of those statements is getting ingested into the aggregated data table. The very nice thing here is that data will actually never leave BigQuery. So these jobs are very, very lightweight because no data needs to flow through those jobs. Here's an example how this works. So as I mentioned before, these processing jobs first will normalize our raw logs. So we have a couple raw logs. We have, in this case, we have a timestamp and then 4 columns. The timestamp obviously is a column as well. It's special in the sense that we partition on timestamps, and the other difference is from a column that we will use this, we will transform this for aggregation purposes. So the first thing that we do in the normalization process is really figuring out like which columns do we actually use. So in this example here, for the aggregated data, we're not using column 3, so that gets filtered out. The next step is we're differentiating between different types of columns. We're differentiating between dimensions and metrics. So dimension is when you write a SQL query, is everything that you group by. So it's your group by clause. A metric is on the aggregation side. So in this specific case, metric is column 4, and we therefore aggregate it together, and it becomes an aggregation to a sum of column 4. So our full aggregation process simplified is we're filtering out the columns we don't need, figuring out what are our dimensions, what are our metrics, and then aggregate on the metrics. The aggregations are defined in SQL, obviously. We have 2 different types of aggregations here. In this example, we have a sum aggregation. We're summing the metrics from column 4 together. And for the aggregate, there's the aggregation count, which doesn't take an input and only counts the number of times one of the group by clauses was matched, or the group key was matched. One interesting thing here is we're truncating on the timestamp so that we're losing the minutes in this case. So this means we get hourly aggregated data. So this is a simplified version of like what's going on internally in one of those aggregation or normalization and aggregation jobs. So to recap what's happening in BigQuery processing, we're reading all of the raw logs from BigQuery, normalize and aggregate the data, and write it back to an aggregated table in BigQuery. Both extraction and transformation are modeled using separate SQL queries. So that means we have a separate SQL query for filtering and normalization, and one SQL query for aggregation. So this allows us to have like a clear separation of normalization or normalizing, aggregating, and then obviously also from ingestion, storing, and serving, because that's done in a completely different technology stack. We're using DML, so think about a SQL merge statement to idempotently write new data in our aggregated table, which makes our jobs idempotent in terms of, let's say, a job failed in the middle of writing. We can just write it again and don't have to be worried about double counting certain aggregates or something like that. And one of the really nice things is like SQL is used here as a modeling tool to model our business logic. So when we go forward in a pure streaming framework, a lot of streaming frameworks, Beam, Kafka Streams do support SQL now. Even if we can't directly use the SQL that we came up with, it's our distilled business logic that we can then use to implement in a streaming framework. So that gives us a very clear path forward. I'm going to hand this over to Steve, who's going to talk about the BigTable and serving.
All right. Thank you, Fabian. So Fabian did an awesome job describing how we get our aggregate data into BigQuery. We're going to talk now about how do we take that data from BigQuery and load it into BigTable in a way that we can use to serve from our serving front end. So in the process of investigating technologies that we wanted to use to do this, we looked through a few of them. One that really stood out was a project called Apache Beam, and then Google Cloud Dataflow, which is a runner for this. So Apache Beam comes basically pre-packaged with a lot of really useful what are called transforms in its lingo that we can use to read and write data from BigQuery and write to BigTable. So immediately, it kind of like removed a large amount of development work that we would have to do to get data out of these systems and put it into the system. Kind of like the busy work that we didn't want to do anyways. This basically allowed us to then focus our effort on actually writing the transformation steps and not having to worry about just moving data around. Additionally, some other nice things about Dataflow is it's fully hosted in Google, which basically means that the data locality is really good. We're reading from BigQuery, which is obviously in GCP. We're writing to BigTable, which is in the same place. So we don't have to worry about pulling down large amounts of data into our own data center and then writing it back into Google. We can just do everything right in the cloud. So basically, the way this works is that we've written a transform that takes a configuration file, defined as YAML, and it uses that to interpret the data coming out of BigQuery. So Fabian mentioned the idea of dimensions and aggregations before. This YAML file basically defines the mapping of those to the BigQuery columns. So we'll take those and we convert them into BigTable mutations. For people unfamiliar with BigTable, a mutation is basically just the idea of like a row key and then some cells that you're going to do something with, either delete or insert or update, things like that. In our case, we've made really sure to ensure that all of the writes we do are totally idempotent. What this basically means is we can run some of these load transfer jobs over and over again without corrupting the state of the data in BigTable. We don't have to worry about like, uh-oh, this load job ran twice, now we've double counted all of the data in BigTable or anything like that. And it allows us to be really confident that our BigTable data exactly matches our BigQuery data. So there's never a question like, uh-oh, like why is this data different if we're investigating data discrepancies or things like that. So why BigTable? For people unfamiliar with BigTable, it's a high-performance, highly scalable NoSQL store. So it basically works on a sorted row key design. So your row key is kind of like your primary key in SQL lingo, and it's sorted lexicographically. Inside of a row key, you have columns. The columns don't have to be the same per row or anything. It's more of just like a tag on your data inside of the row. Additionally, it has a really advanced read API that allows us to construct pretty intricate queries to send to BigTable and push a lot of the predicates and filtering that we would have to do on our end down to the actual BigTable instances. This reduces the amount of data we have to then read out of BigTable and can push some of that compute into the BigTable instances themselves. So now let's talk about how do we actually serve this data now that we've stored it in there. To do that, I want to talk a little bit about BigTable itself and some of the primitives we have to work with. This isn't really anything specific to what we've done, just a little primer. So again, I talked about the row key. You can think of this as like your clustered index, your primary key. It's sorted lexicographically, as I mentioned. Your row key design is probably the most important thing when you're working with BigTable because it will influence how scalable your instance is going to be and how much you can scale horizontally. If you choose a bad row key, you won't have great performance, basically. So within a row key, I mentioned, again, we have column families. And then within a column family, you have column qualifiers. So a column family, just basically a group of column qualifiers. The column qualifier you can think is a tag on your actual data. And the data itself is just kind of binary blobs. It's up to you to define how to serialize your data, how you want to interpret it. You can kind of do whatever you want there. The tuple of the row key, column family, and column qualifier defines a cell, which is your kind of your primitive unit of storage within BigTable. So when we operate on things, we operate on cells generally. So now let's talk about how we've taken that primitives that we get and turned it into a useful storage schema for storing our time series data for analytics. So we'll start with the row key again. We choose the row key based on the dimensions that we've seen are the most common dimensions that queries are going to be queried on. So again, this is important to choose because if you get it wrong, you're basically going to have a very poorly performing query system. But if you get it right, you can really tune for very high performance queries. So again, I mentioned we have a configuration file. In that configuration is defined which dimensions go into the row key when they get serialized. So also something that's interesting to point out is Fabian mentioned how we do timestamp truncation to turn our single data point granularities. We also do something interesting here where instead of storing a single aggregation per row, we'll actually store a large number of time series within a single row. So in our example here with a 1 hour granularity data point, we might actually store an entire week worth of data in the row, which allows us to then actually compress those values together with some compression algorithms that are well-tuned for time series data. This has given us probably a 2 to 3x decrease in the data we actually have to store in BigTable, which has been obviously great for cost, but also really good for performance because we just have to, again, read less data out of the BigTable instance. Dimensions, again, we store mostly in the row key because those are going to be what we're filtering on mostly. But we can also store them in columns for less frequently accessed data. And then finally, the aggregations, again, we mentioned are stored as generally compressed blobs within the row that we've pivoted a lot of them into a single row. So now that we have data in BigTable, we need to serve it somehow. Really early on in this project, we realized that there was a kind of a common theme across the company that people were building very specific services to query the data that they wanted. And they were kind of spending a lot of time doing the same thing over and over again. So one of the things we thought about was, how can we build a more generic query API to query any data set and not necessarily have to have developers build their own services and run their own services just to query one piece of data. So we went out to build a more generic query API designed around querying time series data and doing analytics on it. In building that, we also added support for multiple backend data stores. So we mentioned BigQuery and BigTable as data stores that we support. We also use Druid internally to store some of our data in. So doing this basically allows us to provide our users the decision to make on trade-offs of like, how much do I want my system to cost? What is the performance requirements of it? You can imagine for things that we're doing internal analytics on, we might not need to really worry that much about performance. Maybe 5 seconds is fine for most queries to run, and we're only going to be running a couple queries every minute on it. Druid is pretty good for that and is cheap to run internally. BigQuery is great for huge data sets of multiple petabytes, and we can run queries on them pretty fast in a couple of minutes. So maybe it's OK if users wait a little while for that. The throughput's really high, but the latency is also really high on it too, and we can't run a lot of queries concurrently. But then finally, BigTable is kind of our premier data store that we recommend most of our users of the system use because it's very low latency and very high throughput. We can run many thousands of QPS against it without really any performance impact. So let's talk now, back to BigTable, how we actually take these queries that our serving front end gets and turn them into BigTable queries and then turn them into useful results. So an idea of what a query looks like, we talked about dimensions a couple times. A query will have a filter on it, and then a filter will be a Boolean expression of maybe a few dimensions. You have some things you want to filter on. Maybe I want the advertiser account ID. I want a time range, a couple other things on that. We can take those input queries and using that configuration we talked about in the YAML file, basically build a set of scans of the row keys we want to look at based on those dimensions. We can also take things that maybe didn't perfectly match the row key directly and push them down as filters also into BigTable. We'll take those scans and those filters and batch them up into a few different requests and then send them out to parallel into BigTable. As data starts coming back to our instances, the BigTable API is a streaming API, so we get data basically as it becomes read by the BigTable instances. We can begin doing in-memory aggregation then of that data that's being returned. So in BigTable, we're storing the kind of the lowest level data that we have. The queries that come in might not be on that level. Maybe they're saying, I want the sum of all impressions for an advertiser over a year. We're storing it hourly, so obviously we need to compress it on our end into, or aggregate it on our end into a single data point. So that's what we do here. And every request that's sent out turns into an in-memory aggregation stream, basically, in our service. When all of those partitions complete and are returned, we'll do one more pass of aggregation in memory, and then return that result set to our client. This system is basically what's powering all of our advertiser analytics that we show to our clients and our API users and all of that. So this is one of the larger scale systems we're running here for analytics. To recap, so let's talk about the end-to-end system that we've done and how it matches the objectives we set out to achieve when we started this. So a really important part of this is that the data pipeline we've built is really easy to inspect end-to-end. Because most of it's in SQL, we can easily write SQL queries. And we being developers at Twitter, business analysts, QA people here, anyone can write these SQL queries and execute them against the system to see how the data looks in different parts of it. And it makes it really easy to debug the business logic. Again, because we're using SQL and configuration to isolate that business logic, it really forces people to do that isolation and separate the concerns, which is really important. You don't have your serialization leaking into your query system and leaking into your business logic and things like that. Everything is very well partitioned and isolated. And then finally, BigQuery and BigTable are very performant and very highly scalable, and allow us to be confident that in a couple of years we can scale the system up to 10x, 20x if we need to, and not have to be back at the drawing board and redesigning these systems again.
So another look back at what we presented. We came up with the idea of migrating the batch layer first into new backend stores. So with the idea that we eventually want to bring this over to a streaming system. So how far away are we actually from this? And if you look at this slide and the next generation streaming system, there's really not much of a difference, right? So the big difference is that we will move the processing out of BigQuery into a stream aggregation system. And the processing is completely now defined by a set of SQL queries, which we either can directly use in a stream aggregation system or will be very simple to, will give us very good requirements of what needs to be done. At the same time, we have the data stores and the format already figured out, and it's going to be very easy for us to validate whatever we implement in a streaming system. So for the streaming systems itself, we're looking at a lot of different technologies. Obviously, Dataflow Beam is one of them, but there is still work to be done. This is it.